Very good afternoon, everyone. So, today, right now, we are in the week 8 of this particular course, Technique of Material Characterization, and we have we have completed 40 lectures with this particular week, including this particular week. After this, we will be left with the 4 more weeks. So, in a month, we are going to finish our course, right? So, let's proceed further. Let's try to see what and all the content that has been covered in this particular week. So we discussed about the energy dispersive spectroscopy, ADS, and the wavelength dispersive spectroscopy. Okay, so both are the analytical method, and we were trying to find the composition from that, like the stoichiometric is disturbed somewhere, or the some chemical information we were trying to find some information we were getting. Then at the end we have also discussed about the images in the SEM. Okay, so this were the in the general way in the large scale are the list of the topic that has been covered in this particular week. So before I start going to the okay, just a minute. Before I start going to the lecture, sorry, before I start going to the solving the questions and discussing the concept, I would like to ask you like that: is there any doubt? Do you have any doubt in this particular week, the content that has been covered till now, or anything related with the last week, even the assignments and all? Anything you feel you can discuss with me? Okay, since there is no doubt, let's proceed to the concept which we have to discuss. So now we are going to talk about the EDS, energy dispersive spectroscopy. Right. So what and all we
Here only I'm audible.
yeah, yes, Ahmed, yeah. Go ahead, please.
Yeah. Here I'm totally surprised about that one information
Yeah, yeah, please.
about that secondary electron. We have assumed from the beginning secondary electron for topographic and the backscattered electron for the composition.
Yeah,
Suddenly it is stuck as backscattered electron also it's contribute topography and backscatter electron also will be in the compositional information. But in the beginning, so many lecturers are, if you are Google it also, you will get that
yeah,
secondary electrons for topography, backscatter electron for the atomic composition, it will differ for based on the atomic number. Secondary electron, it will not differ that much on the atom. So this is a what is it most I can say unexpected things I get from the last lecturer.
yeah,
So why in the beginning we learn that kind of things because that any what is that default that the SEM will become with the secondary electron.
yeah,
Um, that's what we received the information. Suddenly it is jump into the no, both are will works for topographic. Secondary electron having some difficulties in some specimen, the backscattered electron having some advantage in some difficulty. So this how you want to comment it?
sure. So again, the information what we have covered till now, it's right, it's perfect. Secondary electron we are using for the topological information, and backscattered electron we are using for the composition, or we can say that the Z contrast. Your concept, the things, what is there in the practical way, it's not changed at all. You are going to do SEM, you want to see the topological contrast, you will go with the SE mode. This is preferred. BSc, it gives the mixed information. It give the information about the Z contrast also. It give the information about the topological. But if your specimen is flat and your concern is that I want to see the Z contrast, how the which elements are there, the brighter one or the having the more element atomic number, the darker one having the less atomic number. This is the BSc mode. Now one can just now in the class we have learned that like BSc one can use for topological as well as Z contrast. But like this is correct. But we know that when we are operating in the BSc mode, let's say this is my specimen. BS, let's say this is the volume which is being created by the SE. Seems like I don't have. I hope it's visible here. So this is the volume which is created by the BSc. Now you can see the spatial resolution. Your probe size is this much. Your spatial resolution is better in which case? It's better in the SE compared to the BSc. Yes, Prahlad, please go ahead. Uh, yes, Prahlad, please go ahead. You have any doubt? You raised your hand.
Yeah, see what I'm trying to, as you are explaining this, for fractography, we get the 3D view, correct?
Yep.
Now we use the AC over there, correct?
Yes.
Now, how AC is creating 3D effect, why BSC cannot do that?
Okay. Uh-huh.
And how, why that AC is using over there, what are the different advantages of that? You can add this also with this point.
Sure. Yeah. So here we have SE and BSc. We saw that SE is the one which is having the better resolution compared to the BSc. Your concern is, let's say, it is the only topological information you want to convey. So what we will you will go with the you will go with the SE. Even the resolution, when we say the resolution of the SEM is around 1 nanometer or 5 nanometer or even less than 1 nanometer, like whatever the range that we say, we are on a larger scale. We are talking about the SE mode, imaging mode, which is contributing due to the elastic scattering. So still, if you are going for the topological information, you will always prefer the SE mode. But if see, we need to understand that BSc can also give some topological information, even though you are not going to use it. But let us say a certain condition has came, some challenges came in front of you, like the SE detector itself is not working. If this is not working, so in that case, you can use the BSc even though you are getting the low resolution. But if your work is getting done, let's say you don't want to go to the very high magnification, you don't want very high resolution, in that way you can use the BSc also. Now it comes with the challenges also. It's not like very easy to use it. You need to know that there are the four elements, and which elements, if you add all of them, it might be possible that the information, topological information, is getting cancelled out. It might be possible that you add two elements, it might have got enhanced. You add two elements, it might have got reduced. It comes with its challenges, right? And that is also, like, one can say advantage also. It's so again, let's say you are doing the factography. You are doing the factography. You know the resolution in the BSc is not good. If your sample is very rough and you are going for the BSc and you want to do the Z contrast, you won't. It's not preferred. You won't be able to get information which is on which you can trust 100% or even 90%. Okay. Now this was the entire thing.
Here,
Like that. Yeah. Yes.
yeah.
Yes.
Here, one more thing. When it is tilting, it is. I understand that both yields are increasing. Is it true?
Yes.
By tilting, commonly if you are saying.
Yeah. Yeah.
But is there is any technological parameters we need to apply to increasing either one, some degrees kind of technology is there.
Uh, Actually, can you please explain your question again? Sorry, I'm not able
By
to.
by tilting, yeah, by tilting, I assume that one both SC and BSc electron yields are increasing.
Yep.
First, my assumption is right or wrong. Comment it. Second one, when I like, because tilting, both it is increasing means
Mhm.
sometimes if I want to get more on BSc rather than SC.
Mhm.
So how technically the tilting I can apply? So it's a trial and error basis, or is there is any formula involved in this?
Okay, your question is very good. So first of all, let's clear one thing. Whenever we are talking about the angle, incident angle with the specimen, you can see that okay, here the angle is made different. The way the signals are coming here, the way the signals are coming are different. So it's like the number of yield. The number of yield is here. The yield is increasing. Here the yield is not that much. Here the yield is more. So by tilting, you can somehow you can make the number of electrons, number of signals to come out, like the yielding will be more. It will be more significant. Okay. So this was the thing that whenever we are talking about the angle, let's say the flat or it's a tilted angle or something like this, yes, it's right that the yield is going to increase, and so you will get the more better information. Regarding the particular value which you have asked, I am not sure, like is there any some particular value which is listed. I will try to go through it. I will try to search the literature if there is any, because I not heard about it. So it might be there, it might not be there, but I'll do one thing. I'll go with it, and maybe in the next week I will try to tell you that whether certain that specific values are there or not. Specific values are there for the EBSD data, I know, electron backscatter diffraction. Sorry, yeah, EBSD. In that way, like people usually tilt by the angle of 70 degree. But for the if you are asking from the SC and BSc perspective, what is the tilt angle? That I have to go and I have to check it. I not went through it. So maybe I'll be able to answer you in the next week. Right.
Okay. Uh, yeah, yeah, good. Then one more doubt I have in stereo microscopy. Also, we are tilting to get slightly two different images to see like two different our eye. So here also I have the same question. That small tilting means uh, what is the angle I can apply? Is there is any control is there by tilting or which side or which angle? Because it may completely go differ if I am tilting, uh, if I am applying my own ideas to tilt, or I need to do trial and error, the stereo microscopic SEM involved, because it's we are getting some 3D differential depth perception of the surface features. One is a direct on the flat, one is little tilt. That little I don't know what is how to measure the little.
Whenever we are saying here about the tilting part, like let's say that our specimen is like this. So this is somehow this itself is an incline. So what we have to overall concern is about that how the yield is going to affect the contrast which we are saying. Okay, something is like little bit upside or hills and valleys are there. It is generating due to the number of yield, the number of electron. Like let's say this. So from this reason, if I am getting more number of yield, more number of electron, in that way I can say that okay, this is appearing brighter. While if this is giving the low, this is so your specimen itself is having the variety of the asperities, so variety of the angle. So depending upon that, it will scattered in the different direction. Okay. So in the essay, you will be able to get all of them depending upon how the trajectories are, and so what we can say is that on larger scale, we don't, in the SEM, whenever I did till now, I don't tilt the specimens. The specimen, whenever we are talking about the tilting and all, let's say this is a grain, these are the two grains, this is the grain boundary. So this grain boundary itself will scatter the electron in some other directions. So I won't be able to see. So the darkness will be there here. This will be the brighter one. So your specimen itself is having variety of the surface roughness, variety of the tilt corresponding to them. So that from that angle we were saying that okay, if the that features is tilted from the particular beam angle, so from the incoming beam, electron beam, how it is going to affect the image. So based on that we are going to get the contrast. Now if you are talking about that the sample itself is we are tilting, so that is something which we have to check, because I did the SCM and I did the SE and I did the BSc till now, and I don't till the specimens. And maybe we are changing the trajectory of the electron beam. It might be possible that. Okay, so I'll do one thing. I'll go with that. I will try to search that. Is there any literature which say that we are going to tilt the specimen, or the disparities which already have. These are the one which are the going to contribute to the yield.
Thank thank you.
Yep.
One slight clarification, because I'm a little bit confused about this four terminology. One is called probe size, probe current, and the pixel size, which is relating or correlating with the resolution and the contrast. But as I understood, the resolution is the opposite form of contrast. But that means if you're focusing on resolution, you need to compromise on contrast. Or you want a good contrast, you need to compromise on resolution. But here, the three factors are supporting to get either resolution or contrast. So I need to first balance that what I need. I need best resolution or the best contrast. Based on that, I need to fine tune the prop size, prop current, and the pixel size. So here, so many formula is there. I'm not able to understand exactly.
Yep.
But open discussion for the practical experience, uh, how we can understand better way for the operating microscope. That's it.
Okay, I've got your fact that like the thing we have discussed in the class, that there are the multiple number of the equations are there, and how the equations are going to communicate with us. That is what like their significance you are asking about, like the probe size, probe current, and the resolutions part, right? So these are the equations that we are going to discuss. We will discuss those things in the upcoming, when I am going to discuss about the few
Okay.
questions. So in during that time we will discuss that. Yeah. So this was the entire thing that like the questions that we are going to ask. Like if any other doubt you have in this particular thing, please let me know.
No, these are all the doubts. That's it.
Great. So now let's try to move ahead. What we have over here from the EDS perspective, energy diffraction spectroscopy. So in the SEM, we have saw that we have the various detector. One we use for the imaging. For imaging, we can say that we use the secondary electrons, or one can also say that for the and BSc electron, BSc detector. Okay. So now we also have the chemical information one can get, that is like the using the EDS, and there is one more technique which is WDS, wavelength dispersive spectroscopy. So now these are the two techniques which will give us the chemical information. Okay, so for example, let's why it is very important to us. Let's say you had the specimen with you, this specimen, which is having the this particular type of microstructure, and let's say that this particular phase is different. These particular phases are different. So these are the blue color one. They are different from the one which is not shaded. Okay. If you did the XRD, you will only get to know that okay, in this particular material, this particular phase one and the phase two are present. These two particular phases are present. But what information you will not get from the XRD is that what are their spatial distribution, where these particular elements are there, whether they are at the grain boundaries or they are in the grain, they are forming their different structure. Those information, the spatial information you will not get. In order to do so, we can adopt this particular techniques, EDS and WDS. So it will tell you, okay, let us say this was the aluminum and this is the copper. So it will give you the difference that, okay, it will tell you, okay, the copper phases are over here and the copper phases are over here and the aluminum phases are over here. So at the end you can get the mapping also. What you will get that, okay, in the mapping, let's say this is the copper phase. So you got the copper phase something like this. So you will get some color over here. Let's say copper, we can assign the black color. And let's say that for aluminum, we can assign some red color or blue color. So it will be shaded. So blue color will be shaded. So you will know that in this particular regions, aluminum is present, or in this particular regions, copper are present. So you can get the spatial, the distributions, how it is done, what is their morphology, how they are distributed. Okay. So that's why the EDS and WDS, this chemical information which we are getting, is very important. Okay. Now how things are detected. What is EDS, like energy dispersive spectroscopy? We had the specimen. We have the specimen with us. We bombarded the electron beam. Now here, along with the SC-BSC signal, we are also getting the X-ray, because now that cascading effect, we have studied that electron beam will come. It will knock out the inner side electron of the specimen, and then to fulfill that, we'll get the from the higher cells, higher energy cell. The electron will transit to the lower energy cell. In the process, they will emit the X-ray or Auger electron. One can say right now we are concerned about the X-ray. Now, this X-ray is the one which we are going to, which is having the chemical information. Sorry, I'm using the wrong pen. This X-ray is carrying the X-ray information, the chemical information. Now, this we can detect in two ways. One, we can detect its energy. Okay. And another way, we can detect its wavelength. Okay. So both of us is going to give us some information. Now here, if we are going to detect the energy part, we'll call it the energy dispersive spectroscopy. If we are going for the wavelength part, it is wavelength dispersive spectroscopy. And we have known that in the class that WDS is having better resolution compared to the EDS. Like it's more trustable. The data is more trustable. So till now we got the picture that the X-ray which is created is the one which is giving this particular informations. Now that X-ray has created, now it's going to the detector. That is something which we are going to discuss over here in this particular entire thing. So this is the X-ray which is going. In front of the detector, we are placing the beryllium window. So it will filter out. Okay, it won't let any moisture and all those things to come. And then it will go to this PN junction. PIN, this particular semiconductor, it will go. It is made up of the silicon. Here it's a P doped and here it's a N doped. Okay. Now, X-ray is having certain particular amount of energy. Specific energy, because we know that the characteristic X-ray has been generated, and that X-ray it will go over here. Now, that X-ray, once it interact with this particular semiconductor, this particular detector, what it will do, it is made up of the silicon. So we have learned in the class that the band gap is around 3.8, I think, in the class. It has been discussed. Please check the value exactly, I not remember. So this much electron volt is needed to create.
Yeah, it's correct.
Yeah. Okay, great. It will create one electron hole pair. Okay. So this much energy is needed to create one electron hole pair. So you have certain amount of energy. The X-ray will be associated with a few keV. So depending upon that, depending upon which material it is, specific energy, like the characteristic energy that you are getting, that is going to generate the number of electron hole pair. And the bias is applied across the P and N. So what you will get that the P, the hole will try to move toward the one side and the electron will try to move toward the opposite side. The moment of the charges is what contribute toward the current. Okay. Now correspondingly, now we can take the information from that. So more number of electron hole pair is generated, contributing toward the more current and all so on and so forth. So particular amount of energy. So the number of hole pair that has been generated over here, this is calibrated with the help of the each element. So let's say for the iron it will be different, for the copper it will be different, for the aluminum it will be different. So the number of electron hole pair that you have generated corresponding to the number of electron the number of the amount of current that has been passed through the specimen, it will correspond for the each of the characteristic elements. Okay, there can be iron, copper, or this. So based on that, it will try to the software will try to analyze that. The analyzer will try to analyze, okay, which element it is, because we have generated this much amount of current. Okay. For example, let's say our probe is right now at the copper. Okay. So now it will try to see, okay, how. So it will this X-ray from the copper will go, and now it will try to create an electron hole pair, and so on and so forth. Will get the current. Depending upon the amount of electron hole pair has been generated, it will correspond to the copper. Now for the aluminum also will be the same thing will happen. So this is the entire mechanism how one generate the X-ray and they detect it. Okay. So before we go to the solving few questions, let me ask you that do you have any doubt whatever we have discussed till now? Yes, Prela. Sorry, yes, I'm.
Here, I like to know why we choose beryllium element for screening that. Is there is any technical reason will be there instead of selecting other metals?
Yep, very good. That's a nice question. That see, first of all, beryllium should have the window should have certain strength. Okay, because we are going to it's going to work under the like the specimen. The SM will be mostly under the vacuum. Second thing is that it should absorb the, let's say our specimen is having the lot of moisture and all. So whenever the electron beam will be hit, the heat might be generated and those moisture will go. So our detector should not get damaged. For that also we are keeping it. Now the important factor is that why, let's say I'm using the beryllium, why not let's go with the platinum, the higher elements, why we are going with the low element only. That the reason is that the phenomena of fluorescence, the X-ray is going to be absorbed if I am going to use the higher elements. Now we'll see that things like R and R, see the energy which is going, the X-ray, the energy which is going, it should go to the detector. It should not get absorbed. So for the higher elements, the energy is start getting absorbed more and more. Now why it is happening, that is something we are going to discuss in the upcoming week, where we'll discuss the phenomena of fluorescence in the X-ray. Okay, and it also depend upon the thickness of the specimen. Like if you keep your specimen quite thick, sorry, not specimen, this window. If you keep your window quite thick, in that way, what will happen that you will your X-ray will be absorbed. It will not pass through it. Okay. So there are the multiple factors, and depending upon that, we have choose the beryllium window. The important one, the fluorescence, so the information about that, the absorbance of the X-ray is the one which is most important over here, and the moisture should not go to the detector, the volatile particles, those things should not go to the detector. That is the reason why we are using the beryllium windows. Okay. uh, Let me know if there is any doubt here, Ahmed.
Yeah, it's clear. It's clear.
So now let's try to solve few questions that we have based the information which we have collected till now. What is the primary function of the semiconductor material? Example, silicon lithium in an EDS detector. So what is their primary function? To amplify the electron beam, to convert the X-ray photon energy into the electron hole pair, to focus the X-ray onto the specific point, to filter out the unwanted background radiation. What do you think? Among these four, which might be the right answer? That's 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 great, Prahlad. The answer option B is the right answer, right? So it is going to convert this X-ray photon into the electron hole pair, right? So that's how we have solved this question. Like we have saw that okay, we are having the an X-ray. After that, we are getting this particular the electron hole pair. The entire process is to convert this detector, the semiconductor, because once it absorbs certain amount of energy, it will go to the excited state, and that Pn and those things we have discussed about, right? So that's clear. Now let's go to the question number two. The key advantage of using EDS within an SEM compared to the standard alone chemical analysis technique is, please pardon. Yeah, yes, Prada. The answer is B. The ability to correlate the composition with the specific microstructural feature, high spatial resolution. So the main part is that spatial resolution. Right, guys? Uh, Everyone, please try to interact. Like if that you face any problem or if you want to answer the question, please feel free to do that. So the entire part that why we are using the EDS with the SCM is that we want some spatial resolution that what is the like the chemical compositions, how they are distributed in the microstructure. That is something which is very interesting for us. So with that, you saw the question number two. Now let's try to go to the next part. The dead time in the EDS. Why spatial word used? uh, because it will give you the space, right? Like it will give you that, okay, this is the, okay, over this particular region, that particular space, that particular chemical composition is there. Over here, this is used. Okay, so different, the thing which I have told you that in the XRD which we cannot do, we cannot know that, especially how the things are distributed, which particular phase is where. That is something which you can do over here. Okay, so people usually try to, what they do, what I usually do, I take my specimen. If I have, if I made something, I want to know what and all things are there. First I will do the XRD, I'll get the phase. But now if my requirement is that I want to see the how these phases are distributed, because see, we know that if some brittle phase is there at the grain boundary, like the mechanical and the structural property, we can correlate with the way this particular phases are, the way this particular the new phase are distributed. Either they are at the grain boundary or they are forming their own different phase, or what it is. Okay, or whether they are just the dissolved in it. Okay, so for example, if you take zirconia and you add yttria to it, let's say 2 to 3%, 3 more percent, what it will do, this entire thing, it will go dissolve in that, it will not form any separate grain. So if you try to map them, you will see that, okay, entire thing zirconia is also there, in this entire yttria is also there. Okay, so this is the word the spatial resolution tells us about. Okay, now here the one thing need to, the question is telling that the chemical analysis compared to the standalone chemical analysis, what are these techniques? This you can say that this is the XRT. Okay, so this is how we have solved the question number two. Rad, any doubt in this? Okay, great. Let's go to the next question. So now, one thing I not told you, in the class we have discussed that, see, there is a time period. There is a time period for which this particular detector is going to collect the X-ray. The electron hole pair will be generated. Now, next thing it will do, it will try to analyze that, okay, among list of the element that has been present in the table, among that which one it is. So it will take some time. So there are two things. There is a dead time is also there, and there is a lifetime. One more term is there. Okay. So in that particular time period, in the initial part, it will try to take the information, take the X-ray, and in the next part, it will try to analyze it. So that is known as the dead time. That's great, Ahmed. Yeah. So what we can say, the detector is processing a pulse and cannot accept the new X-ray photons. So this is the option D here is the right answer. Right. So this is what referred to the dead time. And you can, the opposite of this you can see in the assignment, and you can try to answer that. Okay. Great. Now, here we have discussed about that. Till now we have discussed about the EDS. Now we can discuss about the WDS. Let's try to understand again that we had the specimen, we passed the electron, like the probe, electron probe is there. It interacted with the specimen, it created with the volume of the interaction, and from there we are getting the X-ray. If that X-ray I'm getting, I'm using the EDS. So EDS is like, it will give us, the resolution of the EDS is poor compared to the WDS. It has the better resolution. Okay. So depending upon the question, like if like the comparison between the EDS and WDS, we can say that the resolution of the WDS is far better. You can trust this data, even the compositional, the information which will give it, the stoichiometric it will give, that you can trust it. Okay. Now, what is the difference that they differ on, like what is the fundamental difference between them? Here, the source was there, interacted with the specimen, X-ray has generated. Sorry, let's talk about this. Source, specimen is there. Now the X-ray has generated, it is going to the detector, and now we are with the multi-channel analysis, we have saw that. So now let's say that you have observed that in your specimen, for example, it's aluminum is there, iron is there, copper is there. Let's say these things are there. These things are present in your specimen. This information you got from the EDS. Now let's go to the WDS. The source, again the X-ray created. Now I have the crystal over here. Now this is the heart of the entire WDS detection way. Okay, this crystal is very important. This is a single crystal, and now the thing is that we are already aware about the d-spacing of this particular crystal. Okay, so we know that X-ray is coming, it's going to interact with the crystal, it will diffract. We know that n lambda equal to the 2d sin theta. Now for this particular material, what we are already aware that the d spacing we are aware about. Now the d is fixed. So on what thing the lambda will depend upon? Lambda will depend upon the theta, right? It will depend upon the theta. So now for this three specimen, their characteristic value, their lambda will differ, right? Because their energies are different. Now since their lambda is different, so what it will diffract at different particular angle. Different lambda will diffract at the different particular angle. So now we can see that on there will be the detector will be there, and we can see that at particular theta. So this is the detector. So at particular theta, which is correspond to the iron, there will be the beam. You will see the, okay, here the diffraction is happening. Same for the aluminum, same for the copper, different angles. So this detector will be at different angle, this will be at different angle. So now the thing is that the precision over here is very high, because we are converting the signal to the spatial resolutions. Now again, see how we are going to use. You made your specimen, you will not directly go and you do the WDS. What you will do, you will first know that EDS, what and all things are present. Now once you found that, okay, these elements are the one which are present, depending upon that you will have some rough estimation. You know the lambda, you know the d, you will try to find out somewhere the theta corresponding to each of them. Now WDS will give you the better resolution, it will give you the better information that, okay, these are at this particular theta we are able to detect, just like we detect in the XRD, right? At different angle we get the peaks. Okay, at different angle we get the peaks. So now here we are more or less concerned about that the first order. Okay, so these are the entire thing. So one more thing that people usually get confused is that in the case of EDS, on the y-axis there is an intensity, on the x-axis there is an energy. In the case of WDS, on the y-axis intensity, on the x-axis it's a 2 theta. It's a more or less like the XRD pattern which you get. Okay. So and the resolution of the WDS is better than the EDS. Okay. So this is the entire thing that we have, that we need to understand the difference between the EDS and the WDS. Okay. The core, the entire heart of this particular detector is lie over here, this crystal which you are aware. Now, it's not that we are only using one crystal, multiple crystals can be arranged and they can correspond to the different d value, and so the different element will have the different theta. Okay, so this is the information that we need to aware about. So before we proceed further to solve the questions, please let me know if you have any doubt in this particular sections. Okay, since there is no doubt, let's move ahead.
Here,
Yes, Ahmed.
yeah, here I understand EDS is multi-detector. Number of
Multi.
more detector is present in different angle,
Oh, okay, huh, yeah.
but it is applicable to WDS also. That means
Actually, can you please
more
repeat?
number of more number of detectors are present in one instrument. EDS are present maybe 5 EDS.
In EDS, actually,
Present.
in the EDS, there is only one detector we are using. Here, the multi-channel analyzer are there. So, depending upon the energy that our X-ray is there, X-ray is having, and depending upon the number of electron hole pair it generated, that it will go to the multi-channel analyzer. So, for example, we have the periodic table, right? So, the multi-channel analyzer, something like that, it know that okay, for the iron, how much current need to be should be produced for the copper, how much current should be produced. Okay, so based on that, the amount of energy that has been created, that that electron hole pair are generated, based on that it will try to analyze it. So this is a multi-channel analyzer. So within a one go, within one cycle, you can complete this. WTS is, on the other hand, let's say if you don't know the information, let's say you went directly to do the WDS, you don't not doing the EDS. In that way, you have to move the detector to a very larger angles. So that is the reason why we prefer the EDS to do first, so that you can know that okay, around this particular angle I'll get some information. So let's try to go ahead. Okay. So this is more precise compared to this. Here we are adding the multiple detectors. Detectors we are adding like here. Sorry, not detect. Yeah, this number of the crystal that we are adding, it's more over here. In the case of WDS, because we know that n lambda equal to 2d sine theta, for a different d spacing one can add by knowing the different crystal, we like 3 4 crystal you have, your d spacing will differ. We are intentionally we are putting more and more now. So if one detector you are not using, so another can be the one, like with a with particular, what we can say that yeah. So for example, that certain for certain particular element, your theta is like not in that range of the particular that specimen, that single crystal. You need more or less. In that case, what you can do, you can decrease your d, you can increase your d. So you have multiple 3 to 4 around crystals are there in the WDS, which you can use it. Okay. So the multiple detector which we are talking about, this crystals which we are talking about, detector is remaining same. It's just that this particular crystal which we are talking about, they will differ. So here we are using multiple, and here we are not using any crystals at all. Okay. So this was the thing. Yeah.
I just want query. See, we are using multiple. What will be the advantage of that?
Sorry, Prahlad, can you please repeat again?
Yeah, we are using EDS, a single detector, silicon detector, correct? SIL detector, and in WTS we are using the WTS. Yes, we are using the crystals, correct?
Yep. Mhm.
What will be the advantage of that?
The advantage is that here you are analyzing the things based on the energy, right? So now even the small amount of deviation which is there, let's say the noise signal you can produce. So for example, let's say that from the specimen, you this is your specimen. You created an X-ray. Along with that, there will be multiple other signal. Some noise will be there. That is also can go and excite the that what we can say that our semiconductor, that is silicon lithium detector. While when we are using this particular crystal in the WDS, the phenomena of diffraction, that noise things cannot show. while it will be only for a particular angle. That's why we are concerned that the particular angle. So now since from the EDS you have rough estimation that these are the list of the element that has been produced, that is present. So now you will focus your detector at that particular angles. Now corresponding to that angle, the diffraction will happen only from the particular X-ray that has been generated. So since it is since the phenomena of here, the phenomena which is happening here is a diffraction. Okay. So now the incoming this X-ray beam which has been generated by the specimen, now it's going to interact with our the single crystals, and now with the phenomenon of diffraction it will give the theta, and from there you can know that okay, this is the okay, now you can precisely say that this is the element which is produced, and these are the these are their what we can say the weight fraction or the volume fraction or the mole fractions. Okay, so in that way, like let's say that your what we can say that let's say our starting material is TiO2. You did the WDS of it, sorry, you did the EDS of it. So their ratio should be 1:2, but in the EDS what you are getting that the ratio is little bit deviating, 1:2.5. Sometime you are focusing it's like uh, let's say 0.8 is to 2, something like that. While if I do for the WDS, that composition, that the ratio which information you are getting, it will be more or less very close to it, 1:2.1, or we can say that 0.9 is to 2, so on and so forth. So this is giving more precise. This precision is more there. Okay, so the compositional information you can get from this in more better resolution compared to the EDS. Right?
Here, if you see in EDX, we'll get the peaks, correct? And
Yes.
we get the elements.
Yeah.
In WTS, actually WTS, I have used UDX, and how the WTX data will come, it is will come as a XRD pattern, correct?
Uh, yeah, it will be more or less like that because you will have intensity and 2 theta.
So basic fundamental thing is that in WTS we'll get like a XRD plot type of things, we'll get it,
Yep.
and EDX will get the element versus percentage
Uh,
intensity. For example, I get the TI peak will be there 30%, for example. It will show that how much is their atomic percentage, it will show, or weight percentage. And in WTX, any data you are having, how this thing will be there?
I don't have any data for the WDS. See, whatever the information you are getting in the EDS, the same information you will get in the WDS. It's just that their precision will be very high. Same information you will get. It's like that the spatial resolution which we are talking about, now the spectrum and all, it will be there.
Okay,
Yeah.
thank you.
Yeah. So this was the
here,
thing. Yes, Ahmed.
here, yeah, here both detectors are the rays, the energy. It is the same, or it is two different forms of rays or energies, or we can say it is X-rays, or it is a different, or something called not X-ray or pulse or something. The rays which is going
Can you please repeat again? Sorry, but
here
there was some noise.
from the source. Is from the source, it's we know electron beam and it has the energy. After the specimen to the crystal, one part. Another part is the down, yeah, come down. From the specimen to SA detector. Here, which we received is the X-ray. But after that, from the detector to multi-analyzer, then from crystal to detector, is it the same or different?
Uh,
What it is going?
Here, what we are seeing is that here we are seeing the intensity that okay, at that this particular angle we are getting this much. It is very intense, and now this particular. So what we are getting over here, what we are detecting in the detector is that X-ray. What here we are detecting is in the with the multi-channel analyzer is that the thing which we have discussed, the PNN, like the number of holes and the number of electrons pair that has been generated. Okay, so this is the difference between them. Okay, again the detector will again try to convert that particular X-ray that we is there to the what we can say that the intensity, the number of count based upon the again it will transform that the pulse X-ray signal to the electrical signal, and it will get the information based on that, right?
Okay.
Yeah.
Thank you.
So here, let's try to answer this. What is the difference between EDAX? Okay. See, EDAX is the company name, and EDS is the method, right? EDAX people usually confirm, people usually think that they are the same thing, but EDAX is the company name, and the EDS is the methodology that we are using. Okay, so yeah, let's go with the question that in a WDS system, the specimen, the analyzer crystal, and the X-ray detector must lie on. Yes, Ahmed, that's right. The right answer is option C. Okay, so the specimen, analyzing crystal, and the X-ray detector must lie on the rolled end circle. Okay, so this thing we have learned in the class. Evolved sphere is something we discuss in the TM, and again we are going to discuss in the XRD. Kichi band will be formed in the EBHD. Depth of field and depth of length is not related with this particular thing. So it's a roll-in circle. So you will find that the similar type of question you will find in the assignments. Let's go with the question number 5. Compared to an EDS detector, a, w, a WDS detector provides faster analysis for multi-element specimen, better spatial resolution in the peak separation, a larger solid angle of the collection of the X-ray, low cost and simple. Very good, guys. The right answer is option B. So yeah, Prahlad and Gitu, yeah, great. So the right answer is over here, option B. That the spectral resolution and the peak separation will be there. Okay. Let's go to the next one. The question number 6. Which of the following statement is correct for the WDS technique? Okay. The scan time for the WDS is faster than the ADS. Let me tell you that the scan time for both of them are same. Okay, that dead time, those things that we have discussed about will be the same. There is no possibility of line broadening in the WDS. Third, only one wavelength of the X-ray is detected at one time. Simultaneously, all X-ray of every element are detected. This is incorrect. This is incorrect. What about there is no possibility of line broadening in the WDS. Only one wavelength of the X-ray is detected at one time. Which one among these will be the right answer? Ahmed, that's great. The right answer is option C. Only one wavelength of the X-ray detected at a time. Okay. So here we are going to the diffraction. There is no possibility of line broadening. See, the line broadening will be there. Why? Why it is that particular theta? Let's say that the first, whenever we talk about the diffraction come with the fact that there is a various number of like that order of reflection will be there. Okay, so it might be possible that the order of reflection from the first order of reflection from the iron can merge with the second order of reflection from the aluminum, and they can overlap with each other. It can lead to the broadening, those things and all. It will be there. Overlapping will be there. Okay, so these things, whenever we see that the question is going very straightforward, no possibility. So those will be the wrong one. Okay.
I have seen one picture. I just can share you the link where you see that in WTS and EDS there is a comparison is there. Okay, I just share in that link you see only EDAX is the peak broadening is there, but WTS it is not there.
Okay. See, whenever we are saying that there is no possibility, I don't think that that will be the correct, right? So
Here just I'm trying to understand at the same time the peak.
okay,
Here one picture is there. I'll just tell you that figure uh, 3813B. It is there WTS and EDS like that. Only one picture is there. If you see that,
yeah, here we can see. Let's see.
yeah.
So now here, see, we can see that even though, see, when we are here, we are not comparing the EDS and WDS. Like the question what says that, will there be any broadening in the WDS? The answer will be yes, broadening will be there. Will there be the broadening is more than in the EDS? The answer will be no. The broadening is less than the EDS. So yes, this the information which you have provided over here is right. So here, this one, the EDS is giving the broader peak, while for the WDS, the peaks are less broader. But can we say that there is a no broadening? That is the something which we have to say that is no, it's not correct, right? So this is why like overlapping. In one case, it might be possible that the overlapping is not there, but in certain case, the overlapping might be there, right? So with that, I think we can say that the right answer is option C. Are you convinced, Prahlad? The thing is that no possibility.
Only thing the wavelength. For example, we are doing the WDS analysis. I get the for 10 elements are there. So it will do one by one.
WDS. Yeah, yeah,
I just trying to
yeah, yeah. It will go one by one.
understand physically how it will be there.
Yes.
I just looking for the physical interpretation of it.
Yep. So from the EDS, you got to know that which are the elements present. Now in the WDS, you know what is the crystals, what is that single crystal, that is the reference crystal is present. Based on that, you will try to find the theta. So now different angle you can get that. Okay, you will do it in the sequence manner. Okay, this much amount of this is that, this is that. Okay, so like that we are going to do. Okay, great. Let's move to the next pass, question number 7. Here, a WCR detector filtered the X-ray signal before it reached the detector element, unlike an EDS detector. True, very good. W detector filter the X-ray signal before it reach the detector element. This is there. Yeah, it will filter it out. Unlike an EDS detector. Mm, this question I am not convinced, because if we see from different perspective, it will be like it can be true and it can be false. So let me discard some other techniques are there. In that way, I can do that. So that's why the comparison, the question is whenever we are saying the entire thing, it will be more correct. Okay, this was the question number 7. Now let's try to answer the things that Ahmed has asked initially. Where is the question banks? Now here, the few things we have to understand. Again, the things has already been covered in the class. We are only going to revisit things. And if you face any question in that, please let me know. Okay. So let's say the number of electrons we are getting from the right now we are concerned about the imaging. Now we are going away from the EDS and WDS. Right now we are concerned about the SEM imaging mode. Just a minute, guys. Now, let us say n bar is what is a. Now our concern is about the signal, noise, and what we can say that the contrast, those things. Okay. And what we can say the average number of electron detected from a particular point. Okay. Let's write it. Average number of electron detected from particular point. Okay, so this is the thing, and there is a noise. For every signal, there a noise will be associated with it, right? So let's say the noise, which it's nothing but it's a n, and it will be given by the root over this average signals. Okay, root over n. Okay, so let's say n1, n2, n3. These are the number which we have, the number of signals we are getting. So the average number of electron detected from the particular point will be n1 plus n2 plus n3 divided by 3. Noise will be root over that particular thing. Now we know the contrast. So the feature will only be visible if the contrast difference between them is more than 5. Okay. So, but what is the contrast? Is the maximum intensity which you are getting minus the like S max divided by S divided by S max. So the difference between the, let's say these are the two things. Here I am getting the S max, and here I am getting the S, the number of signals. Okay. So this is how it is defined as. Now the difference between them, this difference should be greater than 5 times the noise ratio. Okay, we can divide it by S max. So the 5 times of noise, this delta S should be greater than the 5 times of noise. Then only we will be able to detect it, divided by the S max, the maximum number of signal. The number which we are getting is that n bar. So now here we can further simplify it, that 5 times this noise, we have defined it as the root over n bar divided by, that is 5 divided by root over n bar. So the contrast will be there if this particular thing, like contrast will be around 5 divided by root over n. This is the n bar, is the number of electron detected. Again, note down that it is the thing which we are talking is about the detected one. So 5 divided by root over n. Now what we can again rearrange the things. I don't know why I don't have pen. Okay, n bar will be what we can say, it will be more greater than or equal to around 5 divided by contrast square. We just rearrange the term. So we'll remember this thing. This is what we have got. Now in the class what we saw, that we are taking, let's say, a certain pixel. Let's say the number of them, let's say around 1000 cross 1000. Okay. This, that is a 10 to the power of 6 frame. Now for one frame, let us say, we are talking about that the how much time it is taking for a particular one frame. Okay, so t, we can define it as a time that beam dwell for any particular pixel, like, okay, for a particular one pixel, that like this is the amount of time that the beam stayed at particular pixel. So now can we find how much time, what is the total time? Can we find that? So let's say f is the total time. Like, let's say we had the image. Okay, so at particular point it stayed around for a particular probe, for a particular pixel, it stayed for t amount of time. So can we find for the this much amount of this much amount of pixel, that is for one we know it is t. So for 10 to the power of 6, we already know that it should 10 to the power of 6, right? So here f is the total time, that the total time that it will take to scan this entire region. Okay, so f is the total time, t is the time which is stayed at particular location. Now, so right now what we have till now understand that this small n, sorry, this n bar is the amount of signal that has been detected. Now the what if we talk about the number of electron that has entered the specimen? N naught, let's say we define n naught is the time, sorry, it's the number of electron that enter the specimen. Let's say I is the beam current. I is a beam current. So I is a beam current. So it means that the number of charge that has been transferred, right? So the how can I write the number of electron that has entered? Let's try to write the number of electron that has entered. So it can be given as the I, the beam current, multiplied by the amount of time, right? So see what we write, the charge that is entered, Q is equal to the I into T. We know, right? This is from the 10 plus 2. So this is the amount of charge that has been entered. But we want number of electron that has been entered, so we'll divide it by the charge of the electron. So what we will get, that is the number of electron that has been entered till now. So till now it's clear. So I multiplied by T divided by number of electron, so divided by the charge of the electron. With that we found that the number of electron that has been entered. Clear? So now from here we can see that this again we are talking for 1 pixel, right? So now if I substitute the value of T from here, that is for the 1 pixel beam at the 1 pixel, how much time will it take to scan the entire region? How much time does it take to scan the entire region? So we can write that in that case I naught can be given as I multiplied by T. I can substitute F multiplied by 10 to the power of this 10 to the power of minus 6 it will become. Okay, I will write T as F divided by 10 to the power of 6, which is given as F into 10 to the power of minus 6. It is divided by E. So this is the number of electron that has been interacted. Okay, fine. Clear. This is clear to us till now. So now the number of electron that has been detected, that is n bar, we have, which we discussed, the number of electron that has been detected, it is given as, it will be equal to the Q times n naught. The number of electron entered multiplied by the efficiency. So like whenever you pass the beam, it not be possible that entire will be come and will diffract out or will be scattered and will be detected. The some factor will be left over, and this is nothing but it is the multiplication of the detector efficiency multiplied by the electron yield. Electron yield, the number of electron that has been generated multiplied by the number of electron that has been detected. Usually this detector efficiency in the case of SE, it is taken as 1. So no need to concern about this. So more or less it will depend upon the electron yield. So for example, we have saw that that here in this case, and while in the case of flat, the yield over here will be higher than this. So in that case, this will increase. For the SEM, for the SE mode, we have saw in the class that the yield will be 0.1 to 0.2. Okay, that is something which we can substitute. Now let's try to put this value over here. So n bar will be equal to nothing but I Q times I multiplied by 10 to the power of minus 6 divided by charge of the electron. Clear? Now also one thing we have discussed that see, n bar is related with the contrast. So n bar, let's go for the equality for a timing. N bar can be written as 5 divided by C whole square will be equal to Q multiplied by I multiplied by F multiplied by 10 to the power of minus 6 divided by, right? So till now it's clear to us. Now let's try to answer few things. We are just going to rearrange this particular, I'm just going to rearrange this equation. I will just keep the I on this side, remaining thing I'm going to change onto the another side. So the current will be given as 5 by c the whole square multiplied by e the whole divided by q f to 10 to the power of minus 6. Right. So this is clear to us till now. So now see what are the factors that has been available here. So we can see that the 5 divided by c, let's separate out the number and the things, number and the variables. 25 multiplied by e divided by q multiplied by 10 to the power of minus 6. This were the constant, this is the f. Now, and sorry, c is also there. Now using this we can answer multiple things. For a particular contrast, let's say we are keeping our contrast to be constant. What if f, that is the amount of time that we are spending to raster the entire thing, if this is high, if this is high, it means that the current which is needed will be low. Okay, so the beam current will be low for to generate the same amount of contrast, the contrast will be same. Now for the other way around, if the time I want to keep constant, then I have to compromise with the contrast, which should not be the case, right? If I'm compromising with the contrast, then like the image can be here and there, like you won't get the good resolution. Okay, so this is the entire thing that we have that we derived till now. So from here we derived the contrast, then the signal to noise ratio we have decided, and then we decide that how much time a beam is going to be located at a particular place, how much time it is going to take to scan the entire region, and we have calculated that also. Based on that, we found that the how much number of current, how much number of electron is going inside the specimen, and how much number of electron that is coming and getting detected. Okay, so these are the two important factors that we have covered. One thing I would like to say that this part, the numerical on this is not been covered in the assignments, so there is a high possibility that it can come in the exam. Might be, like the possibility is there, not high, I don't know what it will be. So this is the entire thing that we have covered till now. Okay, so in this particular entire derivation, is there any doubt that has been discussed? Okay.
So you elaborate the relations between one which is parallelly increased. How to with some examples, some demonstration if you provide, it is easy for us to uh, uh, extract the relations between the factors, parameters involved.
Okay. Practically you want to know. So which example should I take? Mm, mm, I is a probe current. C is the contrast. So if I'm increasing the probe current, if I'm increasing the probe current, that is I'm increasing the probe diameter. If I want to keep the contrast to be the same, in that case what I have to do is that I have to decrease the f. Okay, it means that I have to increase the magnification. Magnification should be increased. Let's see that what example the professor has took. I will also go ahead with the similar example. I think it's been discussed in the which part? Maybe 39. Let's go with the lecture material. Yeah, here it is. Okay, let's go with this then. Yeah, so here the part has been discussed. So let's say we are fixing our contrast. We want the contrast to be the zero point 0.5 only. In that case, the probe size required, like probe size is more or less related with the probe current. Okay, so what we can say that at a particular 0.5, at this particular location, at that particular contrast, if the probe size will keep on increasing. Probe size will keep on increasing. It means that the resolution will keep on decreasing. So we are going to the lower, the more time we are going to spend. So if we spend, if the f is larger, it means that, see, if f is larger, it means that we are going to the f is the time is larger. Frame scan f is varying between the 10 second, which is realistic value for the recording this, which is television scan rate for a given detector. There is a minimum detector. Is there any example given? Although the electron microscope manufacturer builds relatively, it is very important to know that. Okay, the example is not given over here. Mm. So you want something practical, which we are going to do in the
Yeah,
right
exactly.
in the
Practically,
SU. Yeah, practically.
yeah, practically we may interested in maybe magnification, or sometimes we are interested into resolution, or maybe we may interested in the contrast. This is practically we may come to this objective. So at the time, what the presence of skill it is required to fine tune in which area. This is the most important for me to know.
See, one thing is very clear that if I'm talking about the contrast, it will be given by the S max, the difference between the two pixel, like S max divided by S divided by, either you can take that the S max itself. So now, if I want the contrast should be there, it means that I want intense. It should be more intense. No, the intensity should not be. Let's say, let's take up one example. Okay, yeah, now I got one example. In the case one, what we can say that, let's say that the S max and the S. Let's take some value. If S max is, let's say, 500, and let's say S is 400, let's try to find the contrast of it. Okay, so 500 minus 400 divided by 500. Let's try to do some mathematical, and then we'll try to relate with the physically what things are happening. Now let's take the
Yeah,
case 2.
your screen are not visible. What you are writing there.
Please pardon me. Yeah, so over here, this is the case 1. Case 1, we are taking the S max to be the 500, S to be the 400, and the contrast will be given by the 500 minus 400 divided by 500. Now we can calculate it, 100 divided by 500. What it is given as 1 by 5. That is 0.2. Now let's take the another case, case 2. Let's say that S max is around what we can take the value. Okay, let's take the value to be the 50,000 minus let's the value will be the 30,000 divided by the, in this case what we are going to get is that okay, yeah, fine, this will be 20,000 divided by 50,000, 2 over 5. Okay, So this difference is keep on increasing. While the what we have got the value is around again 0.4. Mhm. There is one thing is that when we are talk about the contrast, I'll show you one thing. See, the thing is that if I keep on increasing the current, if I keep on increasing the current, what is going to happen that the entire thing will start to get brighter and brighter. Okay. So along with the signal that we are getting, let's say that let's say that the initial difference is around 500 minus 200, and which is nothing. It will come to comparatively around the what we can say that it will come around 300. If I divide it by 500, it's fine. 500 is fine. Now let's say that I'm increasing too much. Now again that the 4 50,000 it is happening, and in the another case it is happening the 4500, and I'm dividing by the 50,000. In this case, what is happening that the difference is around the difference is around the 5,000, and we will divide it by the 50,000 again. So what we'll get 1 over 10. Here we'll get 3 over 5. Okay, this is the very small. The contrast here is 0.1 and the contrast here is 0.6. Okay, yeah. So this it not happen like this. It don't happen like this. It won't get in the sequence manner. It more or less happen that when we keep on increasing the current, we are keep on increasing. It means that the more number of electron is going to probe our specimen. So more number of electron is going to generate, more number of single is going we are going to get. If you keep on increasing the current, what we have observed that this contrast is decreasing. Okay, so now here we can see that for a particular, let's say we are taking this particular one, this particular. So if I keep on increasing the current, okay, then what will happen? The probe size will keep on increasing. So from the left, if I'm keep increasing the current, it means that the probe size, the probe diameter on an average is going to increase. So from here we are going to the larger side. What does it mean? It means that the contrast is going to be reduced. So that's why a very what we can say the larger current is not preferred. You will go to the smaller current. Okay, but again there is a problem will come. Like it will go to the good resolution will be there. Okay, since you are getting the better contrast, you are getting the better resolution, that will be there. But the problem will be that the number of signal detected itself will be very weak. So you won't be able to detect the signal if the probe current, if the current is very low. In that case will not be. If it is very high, what will happen? The contrast will not be visible the way it should be. Right? The contrast will keep on decreasing. So the thing is that the entire that scenario we can think of that if I'm increasing the current, probe current, what does it mean? That the probe diameter is increasing, and with that we are getting more and more signal that is there. Also we are getting probe diameter is increasing, mean that the resolution is decreasing. More current, probe diameter is high, and large number of current is passing through the specimen, so these things are also increasing. Okay, so I don't have book that right now with me. I wanted to show you, like, this question is very good. There is a book on the TM that sad, I think it's Berry Carter. The first part of it, there they have signified this the difference between these two things. So where in the first case they are telling that if the background itself is getting increased, the background intensity itself is getting increased by the certain value, and so if you keep on increasing the current, the contrast between the two region will not be sufficient enough for you to see, because our eyes is sensitive to certain extent only. Okay, so it might be possible we won't be able to detect this, we might be able to detect this. Okay, so low current is giving the better contrast, high current is getting the poor contrast, But again, the problem is that the give and take problem will be that if low current you are passing, you will get low signal. So signal to noise ratio will be problematic a little bit. Okay. So in that way, we have to compromise things. So now the probe current is high, the probe diameter is high. So what we can say that the contrast will be poor. Okay. So this is how you have to play. It took me quite time to frame things. Yeah. So the probe current, if I'm increasing the probe diameter, increasing the contrast is getting poor and poor. So you have to play. Also, if you keep on decreasing, you tell, okay, if I keep on decreasing the probe current, what will happen in that case? If you keep on decreasing, at the point will come like even though your contrast is increasing, but it will later on it will start to decrease again because you are not generating sufficient amount of signal. So you always have to stay to some particular efficient value, which will uh, which will be in between them. Okay. So with I think this example is it. Are you able to understand? Are you able to get the thing that we have said?
It's wonderful. It's wonderful to understand the current and the contrast. Really good.
Great.
The same way, I like to understand the magnification and the resolution. I think it's opposite. We need to compromise either one. So when
Magnification
we're
and resolution.
going, yeah, when we are increasing the highest magnification, definitely that resolution it will not be reached as we expected. So when we decided to need that resolution means we need to stay with some extent magnification. So here I'm going to the another part, that the current, how it is influenced. That means prob size current,
Uh-huh.
that one how it is influenced.
How the current is going to influence the magnification? I think let's see that week 7 content that we have covered. This was the thing that we have covered. Okay, let me show you. I think we have already discussed about this. Just a minute. Mhm.
First, listing out the factors influencing this tool, I like to understand clearly.
I see you want to know that how the things like the magnification and the current are related with each other, right? That part we have to think.
And maybe working distance also it is influencing the magnification and the resolution as well.
Yeah, yeah. So here we can see that, see in this class, the probe diameter we have talked about, and also we say that if we keep on decreasing this probe diameter, we are keep on increasing the things. Now entirely this magnification, okay, the effective magnification which we are talking about. See, when we are saying that we are magnifying things, what does it mean that we are going to this very small region. For very small region, we are going to see that is something which is known if we are able to resolve it, this is known as the effective magnification. So whatever the factor that we talk about the resolution, the same factor we can talk about the magnification if the things are like if the magnification is the effective magnification. See, whenever we take a pic of someone, let's say you took pic of yourself in your cell phone and you keep on zooming it, it will happen that after a time being you just keep on zooming, but you are not able to distinguish the feature. You are just able to see some box and all. So still, if you are keep on magnifying it, it means that that magnification is not an effective magnification. So there are two type of magnification. One is effective magnification, and one is just a normal magnification which we are doing, and there is no further information. So when we are concerned about the effective magnification, in that case, whatever the things that we have discussed in the week 6, sorry, week 7, this thing, whatever the thing that is going to affect the resolution, in the same way it is going to affect the magnification also. Okay. All you are doing is that when you are saying that I am going to the higher magnification, it means that you are going to a better resolution. The image which is you are going to get, it's a more better resolution as long as it's effective. And the thing that we have discussed till now in the class and in this particular discussions, all of them all of them are just the effective magnification we are talking about. So I will recommend you, Ahmad, that this part that we have covered in the week 6, which is related with the resolution, and also week 7 we have discussed that. In that also we have discussed these things. So because of the time limitation right now, we only have the 30 minutes left. So I can cover that part, but it will take more time. So let's can you go with that, and we can, if you have any problem in that, we can discuss again.
Okay.
Yeah.
Okay.
So I'll do one thing, that I will make a good slide next week to explain these things. So in maybe in the 5-10 minutes only, we will be able to explain that the entire part. Right now the slide I not made the properly. But the thing that the content that we are talking about, we have already discussed that. So now I have how many questions is left? A lot. So see, now our concern is about this particular equations. Okay, this is the thing that we have discussed. Now let's say this part. For two adjacent phasor to be distinguished in an ICM, the difference in their signal must be greater than, the difference between the signal must be greater than A, B, C, or D. What do you think? The average signal, the 5 times the noise level, the beam current, the frames. So what we have talked here, what we discussed that, yes, very good. The yes, I mean, it should be great more than 5 times of the noise rates, right? So the option B here is the right answer. Okay. So yeah, we have solved this question number 8. Let's go to the right. The critical beam current required to achieve a certain contrast. So the what we are saying is that the contrast is fixed. If you are fixing the contrast, which factor is going to affect? The frame scan time is increased for a critical beam required to achieve the certain contrast level increase. So IC, when under what condition IC will increase? Okay, this is something which we have to answer. If I'm increasing the I and the contrast is fixed, what does it mean? It means that what we are doing is that we are decreasing the scan time, right? From this equation we can say that if I'm increasing the current, keeping this is already a constant current, this contrast is already fixed, certain contrast is fixed. So what does it mean? That only the variable is f, so that it can be done by decreasing the scan time, right? So the option C over here will be the right answer. Okay guys, yes, Emma.
I thought it's increased. It's become decreased.
We are talking about the scan time.
Each pixel, I mean each pixel, right? So each pixel the beam is scanning.
Not on one pixel. F F is for the entire thing. The small t is for one small pixel. So we can see that where I've discussed this part, small t, and yeah, see, this small t is to probe a particular small pixel. F is to scan the entire region. 10 power 6 we added because we took the region about 10,000 multiplied by 1000. Okay, so this is how we took it. Now let's see, you fix the contrast. Now let's try to understand Ahmad in this way. Your critical beam current required, if I'm increasing the beam current, IC is increasing. What does it mean? It means that more or less I'm increasing the probe size. Probe size is increasing. Contrast I'm keeping constant. What I'm changing there? I'm changing the scan at which it is happening. You have the larger probe. The probe, initially the probe was small. You will require larger amount of time to scan it. While if you have the larger probe, the scan time which you will need, it will be low, right? So, so you, since the things we are fixing, remaining thing we are fixing, we need to balance out. So if I'm increasing, the probe size is increasing. If the current is increasing, the probe size is increasing. What does it mean? That the your pixel, the each pixel size will be increasing. Right? Good. That's great. So now let's go to this question number 10. What is the primary source of contrast in the topological imaging mode in SEM? What is the primary source of contrast in the topological imaging in SEM? It seems like I missed one particular. Something is missing. I needed to discuss one more concept over here. Okay, so Ahmad is saying that the option B, yes, that's the right answer. Option B is the right answer. That for the topological imaging, we are going with the surface height and the roughness. Okay, so this is the one which is going to electrical conductivity. No, the crystal structure is not. Z contrast is not going to go for the topological information. Okay. Okay. Why does a tilted specimen appear brighter in the SC image? Why does a tilted specimen? See, here it's specified. From the tilted, it means that the hill appear brighter in the SC. It has a higher atomic number. The secondary electron yield increase with tilting angle. The detector is more sensitive to the tilted specimen. None of the above. Yeah, that's great, Ahmed. The right answer is the option B, because the yield we are increasing. It's the yield that is matter over here. So the option B is the right answer. Great. Okay. So now here, how does the interaction volume change when the specimen is tilted? If I was having the specimen like this, when like the specimen was the surface was flat. In another case, I'm having the surface which is like this, and the electron probe is coming. So how these things are going to change? Will it change the depth and the width? It will change, or it will remain same? What is going to happen? Its shape and orientation related to the beam remain unchanged. It become larger and shallow. It rotate to the specimen remaining aligned with the specimen surface. It disappear entirely. Okay, so here the thing is that they are not going to change. If you tilt the interaction volume over here, the interaction volume over here, the depth and the width which was there, it is going to remain as it is the way it was. It's not going to change at all. Okay, so here the right answer is, that's very good, Ahmed. Yeah, so the right answer is option A. The shape and the orientation related to the beam remain unchanged. Okay, it's just that when you are tilting, your yield is increasing. That's the factor. Okay. Okay, let's go with the next part. 13. A key difference between the scanning electron, sorry, the key difference between the secondary electron and backscattered electron detector for the topographic images. For the topographic, what is the key difference between them? BSC yield is sensitive to the atomic number, while BSC yield is not. BSC detector are sensitive to the trajectory of the electron due to their directionality, while SE detector are not. SE image provide better spatial resolution at the low magnification, while BSC is better at high magnification. None of the above. Is BSC is better at the high magnification? No, right? The BSC is not better at the high magnification. See, higher magnification, right? So we cannot use the BSC at the high magnification. The reason is that the spatial resolution of the BSC is not good. It won't go to the higher magnification. The SC is the one which can go to the higher magnification. So option C we can rule out. Right. Now let's go with the A and B. Let's read again. SC yield sensitive to the atomic number. Is secondary electron yield is sensitive to the atomic number. What do you think? The option A is right or not? True or false? Let's take it as a true or false. A is no, right, Prahlad? That's great. Option A is not. The B. BSC data are sensitive to the trajectory. They are sensitive to trajectory of the electron due to their directionality. Okay. While acid detector are not. See, acid detector, see, they both are topological. They both can give us the information. The way they are giving information are different. If I have the, let's say I'm talking about the SC, the electron is generated over here and these are generated over here. Okay. So if I here is a detector, so what it will do, it will capture all of them. It will capture all of them. The acid detector, that is a ED detector, it will capture all of them because of the field which is applied to it. So that the fact of directionality is not here. So all the direction it is capturing. While when we talk about the BSC, what will happen in that case, that they have the strong energy. Okay, they have the strong energy. You cannot deflect them. They will go. So BSC detectors are sensitive to the trajectory of the electron due to their directionality. Okay, so if let's say sample is flat and we are generating some BSC over here, so it will go. But let's say that the sample is a little bit not flat, so it will have some electron beam probe over here. What it means that here the electron will be will get more and they will follow certain trajectory. We won't be able to detect it, deflect it. Okay, so these four elements which we are having in the BSC, they are the one who is going to contribute towards the each of these particular signals. Okay, so the topological information that we are getting in the BSC is different from the SC is due to the directionality. This direction factor was not there in SC because we can capture all of them by applying the bias across the detector, that metal cage which we talked about last time. Here we cannot do that. Okay, so the right answer is B. Okay, great. Now let's try to answer one more. The primary reason the BSC detector is used for the composition contrast is that their yield. Why we are using why the backscatter electron detector are used for the compositional contrast. That is Z contrast we are talking about. It's highly sensitive to the accelerating voltage. It generates from the inelastic scattering and electron cloud increase strongly with the atomic number of the element. None of the above. What do you think? What is the right answer over here? BSC. Why we are using it for the Z contrast? Z contrast means that the atomic number contrast, right? Yeah, that's right. I'm at the end. Yeah, great, brother. The right answer is option C. Because BSC signals are sensitive to the atomic number. More atomic number, larger the atomic number, more and more are the atomic number, the backscattered signal will be more because the nucleus will have more strength to scatter this electron back, the primary electron back, and make it to the secondary, sorry, backscattered electron. So the right answer is option C. Only two questions are left. We'll finish it. So yeah, the inherent compositional contrast between the two phases in BSC image is likely to be very low if inherent composition contrast. This composition contrast between the two phases in BSC image is likely to be very low. Under what condition? The phases are made of the element with very different atomic number, very similar atomic number. Multiple element is multiple. A multi-element detector is used with all the segment active. BSC is not sensitive to the composition contrast. So these two will directly cancel out, right? Yes, Ahmed, that's right. Yeah, the right answer is option B. BSC is giving Z contrast, that is Z1 and Z2. If the difference between them itself is very low, so the contrast will be low. While if the difference is high, so the contrast will increase again, right? So the composition contrast will be more. So that's why if it is very similar atomic number, we won't be able to. Okay, the image is likely to be very low if the contrast, the two phases likely to be very low if. The option B is the right answer. Okay, Prahlad, is it clear? This part? Yeah, great. Uh, to solve this last question, I prepared mm, one slide I prepared, but I don't know where it is. Okay, let's see it in my PPT itself. Yeah, over here. So see over here. This is the SE part which we have already talked about. So here we are getting more yield, here we are getting more yield, here we are getting less yield. That part we have discussed. Now the BSc has the four different elements. Okay, four sections it is having. So we can see that okay, let's say this particular image it's having some particular contrast, and now this contrast is coming due to the topology. Now let us say someone want to see the like this is detected by the four different section of this particular BSc detector. First we can say let's say this, the second one is over here, and this third one is over here, the fourth one is over here. Now someone want that they want to see the topological information more enhanced. In that case what they will do, they will add this two detector, combine this two detector and see the image. In that case what will happen, this will be enhanced further. Now let us say you want to see the information in a way that you don't want topological information, then what you will see, you can see that there is a depth is over here, while there is a it's a like little bit uplifted. If you add this two, what will happen, you will see the flat surface, you won't see the topological information over here. While if you add this two again, in this case again you will get the topological information. If you add this two, you will get the compositional information, right? If you add this two, you are removing removing the topological information. So you have to be very careful whenever we are saying now that okay, see, people, whenever I go for the FES and do the EBSD, I don't do all these things. I don't say okay, give me the four different element and let's see. What I make sure is that I take my specimen, I make it flat. I will polish it and I will make it very flat so that there won't be any topological information. The contrast should not be topological. Other than that, the grain boundary, if I'm etching it. So in that way, I can remove this topological information. What will I get? I will get only the composition information. In that case, I can use all the four detectors or any one detector at a time. Anything is fine with me. Okay. So this is how the entire thing about the BSc detector. Okay. Uh, Let me ask you any doubt in this particular section. Okay. Since there is, yes, Ahmed, please go ahead.
It's everything is clear.
Yeah, please go ahead.
It's clear, clear. All is clear.
Thank you. So let's try to answer the last questions. It is a true and false, and like this itself has the multiple question in it. The spatial resolution, the spatial resolution of the topographic image in the BSc mode is better than the SC mode at high magnification. What do you think? Which one is better? BSc or SC? Is it true or false? The spatial resolution of the topological image, we are talking about the topology, is better in the BSc mode. It's telling that the topological information is better in the BSc mode and not the SC mode. Very good. The right answer is false. So SC mode has the better resolution compared to BSc mode. That's great, Prahlad. So see, Ahmed, it's that is this is the main reason that why we are going with the SE, not the BSc. When we want to see the topological information, we will go with the SE higher magnifications. Okay, so this is how we have solved this first part. Let's go to the second part. Using only one segment of the multi-element BSc detector enhanced enhances topological contrast by creating a shadow effect like the directional lightning using only one segment of the multi-element BSC detector enhance the topological contrast. So what it's saying that, let us say we have this. I'm only using one of the detector. I'm using only one detector. This. I'm not using the another. In that case, what will happen? I'll see the topological information, right? So this is what it's saying. The question is saying this only. Like let's say I'm only using this. I'll get this information, topological info. If I'm only using this, I'll get this. Right. So this is what our question is saying that using only one segment of the multi-element PSC detector enhances the topological contrast by creating the shadow effect, like directional lightning. So is it true or false? It's a true, right? Very good, Pellam. That's great. Now, the see, the secondary electron yield is more sensitive to change in the atomic number than the backscatter electron yield. More sensitive to change in atomic number. What do you think? Is SE is more sensitive to atomic number or BSE is more sensitive? Is it right or wrong? False, right? Very good. Great, brother. So whenever we are talking about the atomic contrast, SE is not coming into the picture. Only the BSE is there. Whenever you are talking about the topological information, even though SE, BSE, you can use both of them, but when you are going to the higher magnification, it's always that okay, you have to go with the SE because the resolution is not that good in the BSE mode. So more or less, on the larger scale, like everyone, use the SE mode for the topological information. Now that's D part. BSE is not sensitive to the compositional contrast. Or false. Right. Yes, I am right. The here it is false. Great. So these were the list of the questions that we have covered. Let's. There was. I would like to discuss one thing. Last time that. Yes, yes. Please, you go ahead first.
Practically, I don't get clarity that shadow effect using only one element or two or three. How I can decide how many element I need to use to get to that right.
See what is happening. Why this the shadow has been created over here. This reason, like I'm using which detector? Let's say I'm using this particular detector. If the shadow has been created, it means that the directionality, since see, this is our basic detector. Okay. Now, from a particular location, we saw that few of them are coming to this detector number 3. Let's say this is the detector 3. Okay. So that particular region will be brighter. But another section, like from for that same thing which we are getting bright over here, it will be darker for this case because it got scattered. So the shadow which has been created over here, it is because because it has to do with the directionality. Due to that particular cavity or that edge, the backscatter electron has scattered in the different direction which is not been detected in your this detector. Which is might be possible that it is detected in the another detector. For example, you can see there this part is having the shadow. It means that the present detector was not able to detect this. Present section of the BSC detector was not able to detect. While here we can see it's a brighter. It means that the more number of electron we are able to detect in this particular section. Okay. So this is how the shadow effect will be there. If the electrons are deviating from the path, if electrons are deviating due to the surface feature which is available, then the shadow will be created. If not, then this bright things will be created. And you can also see the fact that this bright region is far more brighter than this particular gray type of region. Okay, this means that the more number of electron has been covered. What does it mean? That it means either we are something somewhere the feature is something like this, or the feature is something like this. Okay, so from here we are getting the more number of the yield is more. Okay, and that yield is detected in one of the detector. In another detector which was not able to detect them will appear as a dark. Right, Amin?
But here, why we are interested to get to the shadow effect? So shadow is giving something wrong direction to us, right?
It's nothing like a wrong direction what we can say that. It's just that the present detector is not able to detect this because the direction is deviating to the different section. It's like the cavity is there or something is there which is deflecting. Let's say the grain boundary itself can be sufficient enough to deflect the beam somewhere. Okay, so in that case this scattering which is happening, which is leading to the change in the direction, this will contribute toward the contrast. Okay, great. You have one more class to attend. It will start from 5. I think we have to wind up right now. I had few things to discuss. I'll continue the things in the next week, let's say the week 9. And I have couple of things to do. Like the Ahmed has told that the magnification part, I will do that part. And I think one more thing that me and Ahmed we talked about initially. Ahmed, can you remind again? What was that?
Yeah. So that is when tilting, both are increasing, the yields are increasing.
Yeah,
But
particular angle.
we prefer to, yeah,
Yeah.
yeah, we prefer to one electrons, for example, secondary electron compared to backscatter. So that time, what we need to do, that's the question.
Okay, that tilting part we need to be that particular angle you want. Is there any particular efficient angle at which it have
Yeah,
occurred
yeah.
better? Yeah. So these are the two things. I'll prepare the slides accordingly. And today we extend too much. I think the class has might have started by now. Okay, guys. We can wind up for this particular session. I have few more things to discuss, but we'll continue in the next class. Okay. Bye bye.